This is part C of a three-part talk. There were two types of devastating tsunamis in the 1964 Alaska earthquake: a tectonic tsunami that propagated across the Pacific Ocean, and local tsunamis caused by shaking-induced submarine landslides within glacially carved fjords. This part C pertains to the local tsunamis. The interlude at the outset here is to discuss glacially carved landforms, with some of the world's most famous ones from Yosemite Valley, California. And here's Yosemite Valley, just a stunning view of this classical U-shaped valley with steep walls and just stunningly beautiful, but geologically really impressive to think about how they got here. Here's another view from Glacier Point, this trail above Union Point, an older photo, but again, this really stunning shape of steep valley walls. How did they get there? So the two things to imagine here is fill this valley with ice to envision the final glaciation in this region. Or you can also fill this valley with water to envision the shape of deep fjords in coastal Alaska, such as those involved in 1964. So whether above ground or below ground, we have the influence of glaciers on landforms. And here's from a 1987 book about the geology of national parks here. Shows a V-shaped valley of a river. Here's the V, modified by water erosion, then modified by ice. You see it's kind of more like the Yosemite, filled in with ice here, carving away with rocks, material grinding as this ice flows downward. And then when the ice is gone, you have this U-shaped valley. So that's kind of the cartoon picture that in Yosemite Valley, the ice is no longer there in these valleys, although it is not too far away in remaining glaciers. In places like Alaska, the ice is still there in a lot of places. I really like this picture from a 2019 paper, view to the south from summit of Forsyth Peak, showing features mapped in the field that were used to help determine Tioga Age ice extent in Yosemite National Park. And so here's what the geologist is seeing, this sort of rugged crest, looks like a dinosaur back or something, snowy peak here. And this is what they're envisioning is the thickness of the ice here shown of this ice sheet, the direction of the flow, and the part that the ice sheet never eroded. Everything else below here has been carved down by this movement of ice. And this shows from the 1987 summary book, Tioga Ice Field and Valley Glaciers showing maximum extent during Tioga glaciation, the last major glaciation in the Sierra Nevada, which peaked about 20,000 to 15,000 years ago. And so it shows this is pointing toward the east here. It shows all this ice that is now gone. So Half Dome, Yosemite Valley, they're shown as having ice filling in all these modern valleys. So what was the setting in southern Alaska, in this case, Prince William Sound, 20,000 years ago? Where is our Yosemite Valley today? And the way to think of that is, well, it's either underwater or it's still under ice. We have lots of ice and ice sheets and valleys filled with glaciers on land, but the ones we're most interested in the sake of the 1964 earthquake is looking at this picture. And this is showing the detailed bathymetry. So this is the coastline. Red would be very shallow water, and this would be the deep shore, offshore, a couple kilometers deep seafloor. And then this would be the continental shelf. But what you see is these like channel-like features in blue that show where these glaciers tongues extended during the last glaciation. So LGM stands for the last glacial maximum about 20,000 years ago, and that's how far the ice got. So the ice sheet at that time, blazed down here out in the modern ocean now and carved its way some pretty deep channels. And so these carved out ice channels are called fjords, and they will be the focus of this talk and we'll see why they are so important. So we have the sort of underwater view of where the glaciers were 20,000 years ago. This would have been ice. Fill it all in with ice, carving away at these structures down below. That ice is gone from this region, but it's not gone from regions above land here. If you look in Google Earth, you can see that the snowy regions are some combination of glaciers or ice sheets. But we can see huge precipitation, high latitude. There's a lot of ice and glaciers. Even as they may be retreating today, there's still a lot of ice. And so here are some of the places we'll be looking at: Valdez, Chenega, Whittier, Seward. But the main point here is that we still have a lot of ice above ground. So that's our intro, thinking about how these landforms are carved by glaciers, and particularly the ones that are underwater. And we'll see more detail on these fjords in different regions. So here's our second type, the local tsunami. This is caused by submarine landslides initiated by earthquake shaking. This is different from the seafloor lifting up across the large, broad region and causing a tsunami that propagates across the ocean. It's very different. It's the shaking from the earthquake that causes a landslide from a fairly unstable, steep slope. Here is a tabulation of deaths from the 1964 earthquakes from within Alaska. So we come back to this to think about how people die in terms of what are the hazards. The timing of the earthquake undoubtedly contributed to the low casualty rate. It was a holiday. Many people who would otherwise have been at work or returning from work were at home. Schools were closed for the holiday. In coastal areas, the tide was low. Had tides been high, inundation and destruction by sea waves would have been much more severe. Nevertheless, sea waves caused more deaths than all other factors combined. So we saw that from an earlier table, part A, that it was the tsunami waves, and in particular, the local tsunami waves, that caused the majority of the deaths from 1964 earthquake. Here's a compilation of information from a document on tsunamis throughout the history of Alaska in 1996. And I'll draw your attention. This is Prince William Sound. This is land. This is water. And these are the fatalities and tsunami run-up heights. So in the magenta is giving the fatalities, Valdez, Whittier, Chenega, Seward. And the orange is giving the height, the run-up height. How far, what elevation did the tsunami wave reach? Giving you some idea of, if you have buildings below that height, they would have been severely damaged and could have been debris, being moved around with the wave as well. So these are some of the 4 areas we'll be focusing on. This shows a more modern study looking at the 4 areas, a summary showing the fatalities, the maximum run-up, and really pretty staggering: 30, 67 meters, 20 meters. These are, you have to imagine, in these shallow regions, if that is an elevation that the tsunami is reaching, it's a very gradual coastline. That means the wave is going very far inland. Okay, so this is our locator map. We have Valdez, Whittier, Chenega, Seward. And while it may look like this label has been misplaced, it's intentionally that way. The modern village of Chennai is here, which you'll find in Google Earth, but in 1964, it was situated here. And it was the massive destruction and loss of life that caused people to abandon the old site of Chennai. So let's look now toward these, where these appear in Prince William Sound. We have Valdez, Whittier, Chennai, and then Seward just off to the west. And this map is giving us a reminder. These are coastal communities. They also have deep. So these are in meters. The blues are over 100-meter. Many of these are sort of 300 meters deep fjords. So very deep water, as anyone knows, going, whale watching in these places. It is the ocean in terms of depth. It is not, this continental shelf area of tens of meters. It's deep water in these places. And that turns out to be critical for the generation of these local tsunamis. So we'll start with Valdez, shown up here at the end of the road, and the beginning of reaching out toward Prince William Sound. I'll show the locator map, and then I'll show you the best information on the bathymetry, the detailed topography underwater in each of these bays. So the community is Valdez, the bay is Port Valdez. In 1960, population at the census was 1,000. 13 deaths from the 1964 earthquakes occurred here. This shows a map, and you usually have a colored map, and the water depth in the purples here, 275 meters. So it really is a steep drop. So when I look at this, I'm thinking something, along the lines of a Yosemite Valley, steep carved valley. In this case, it's filled in with water and carved out by glaciers. And so this shows the old Valdez, which was relocated following the 1964 devastation. But this is kind of the geometry, and we'll see some common themes going from these different places. This is a photo showing the destruction from the tsunami, and basically keeping in mind that this earthquake happened in late March in Alaska, where there's snow on the ground. If you don't see snow on the ground in this area, that's where the tsunami reached. So in some sense, the photo gives a remarkable picture of the inundation by the tsunami. Just this line shown in here shows the extent of this wave. And we'll see more about the damage related to the leftover docks. We can see these tanks shown here, and we'll see different perspectives of what was left in this section. It's important that it was known in 1964 that there had been tsunamis caused without earthquakes in these regions. So that would be sort of a different local tsunami. We've been focusing on ones caused by earthquake shaking, but you don't have to have shaking to have the instability of one of these events. So the record shows that on at least 5 occasions in the past 70 years, 1899, 08, 11, 12, 25, submarine slides and associated turbidity currents have accompanied earthquakes at Valdez. So actually, in this case, they were associated with earthquakes, but they don't always have to be. To this extent, the combined effects of the earthquake of March 27th were in no way abnormal. And the combined effects being tsunami from the tectonic tsunami come in, as well as shaking and also submarine landslides. Instead, they typify a reaction pattern under seismic conditions that may be expected in the prism of a saturated fine-grained deposits that make up the Valdez Delta. So this is now getting at the nature of all this sediment that's being shed out into Resurrection Bay by this river delta is contributing to the conditions that cause so many of these submarine slides, but the biggest and most devastating one occurring in 1964. So here's a picture, Bradford Washburn photo, Valdez in 1937. You can see this massive river delta, and it almost seems like this community is bracing itself from the river plain going back and forth in this region. It would seemingly not be a great choice to put a community, but you can see it's here. You can see it, the road coming in, and these would be 2 of these docks coming out into the bay. And just from this photo, kind of crummy black and white photo in this rendering here, but you can see the mystique and grandeur of this place. This is an image of Valdez, aerial photo showing the small community, the streets. You've got this river plain on both sides, shedding sediment out into this area and forming some of this unstable shoreline shown here. But keep your eye on these two docks here. This shows after the 1964 earthquake, so before, after, and you can see all kinds of missing pieces there. You can see these oil tanks here are still there after the earthquake. Sorry, before, after, but much of the coast area, the docks are gone. This is a sketch which I think does very well to show just what happened. Here are docks and structures out there, and they're dotted lines because they're no longer there. And this huge chunk of coastal area underwater just slid down and out into the bay. And when that happened, things fell out from underneath, and this generated tsunami waves within the bay. And this was not the only one. There have been many detailed studies trying to understand exactly what kinds of submarine landslides occurred, but this is probably the most notable one in terms of causing death and destruction for this community. Here's a study from 2014, really trying to understand. Here again is one of these docks shown here. Here's another one of the docks, trying to understand the exact sequence of part A. Docks start to collapse. The Chena, which is this boat here, breaks free, lays over to port. Part B, shown here, says Chena pushes into small boat harbor. So here's the Chena into the small boat harbor right here. Chena briefly grounds. Part C, Chena possibly pulled south, possibly destroying a second dock. And part D, it says slide scarp evident. Water can be seen flowing over the edge of the scarp. So there's some somewhat challenging video footage of someone who had taken footage. The originals are not well preserved, but trying to piece together from eyewitness accounts and the limited video footage what happened. For example, these three tanks inferred to be looking toward the shoreline here in the video footage. But at any rate, this motion of the wave caused the loss of life with people from the dock associated with the large movement of the boat and the tsunami waves. Shifting west toward Whittier, shown here. So we have our locator map, Prince William Sound. Whittier also has, the community is Whittier, the bay is Passage Canal. 1960 census population was 70, 13 people died in Whittier. And this shows, again, depths of, in this case, the lows here are at 358 meters, a couple hundred meters. So typifies these fjords that we've seen here associated with submarine landslides and local tsunamis. So down here is the community of Whittier with respect to Passage Canal. Here's a kind of photo just often trying to impress the force of the tsunami waves with regard to practical objects. You imagine trying to ram something like a 2x6 through a tire. It's an impressive action there. This is almost a Hollywood scale image of the oil fire occurring nearby the shore. Again, where you don't see snow is where the tsunami went. The dock area, tank farm, and railroad facilities were severely damaged by surge waves developed by underwater landslides in Passage Canal. The waves inundated the area of darkened ground where the snow was soiled or removed by the waves. Here's a map. It's a little harder to piece this together, but here's Whittier at the bottom, Passage Canal, and this is a geologist trying to map out the direction of the wave, the inundation, and where these landslide areas were. So this shows some of the inferred landslides going underwater in this case. And we'll look at a cross section of the fjord to get a basic picture of what's going on. Post-earthquake submarine topography. So after all these landslides, you have a new kind of bathymetry, wave height, wave direction, submarine ruined areas, and profiles. So here's a profile across the fjord here from C to C prime, and you see the pre-earthquake profile and post-earthquake profile. We'll zoom in on this, and you see that before it looked like this, and all this land through the shaking of the 1964 earthquake let loose. It's just too steep to handle, and it wants to send it down to lower regions. And so it created this landslide occurred, and the material kind of was redeposited down below. And that action of moving mass underwater created the local tsunami, and those waves that bounce back and forth caused the destruction and loss of life. So earthquake shaking causes a submarine landslide, which generates a local tsunami wave and permanently alters the profile of the fjord. The land surface is changed. Moving to Chennai, this is the site of the Chennai submarine landslide and loss of life. And just to give if you look in Wikipedia, this is where Chennai Cove is, and the original Chennai village site in 1964 on Chennai Island. And this is the modern community of Chennai, moved by some 40 kilometers or so. And this gives in Wikipedia just a brief history of that. And really one family moving there, and in the 80s, 26 other families migrating to this new location known as Chennai Bay. Here's a study from 2016. Again, keeping with this theme of the bathymetry, it's the geometry nearby these communities that led to the devastation in terms of loss of life and the local tsunami waves. So here's our water depth, the blues being 300 to 400 meters water depth, carved out by glaciers in the past. The bay is known as Dangerous Passage. The 1960 population was about 80, and 23 deaths. Almost a third of the population occurred, just devastating, during the 1964 earthquake. And so this is where the Chennai Village community and Chennai Cove, this little notch right here. This is an aerial view photo taken 2 days after the earthquake. Aerial view of Chennai Village site at the head of Chennai Cove. Lower limits of snow as shown by the arrows here, 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 indicate the approximate limits of wave run-up. The schoolhouse is circled. The schoolhouse is on slightly higher ground, but the devastation is staggering in the community right here. Main part of the Chennai Village site, piling in the ground, marks the former locations of homes that were swept away by waves. Schoolhouse on high ground was undamaged. So submarine landslides here caused local tsunami waves and led to the significant number of deaths from the entire earthquake. This shows a map of the distribution and intensity of wave damage. And so these numbers shown here are these are in feet here. These show the elevations, and this marks how far the tsunami wave reached. So the run-up would be at 69 feet elevation. So that doesn't mean it was a 69-foot high wave. It just means that within this large distance here, the wave covered all this ground, and to get to this height must have been appreciably high. This shows the photos we're looking at. This is Chennai Cove, so the real massive destruction, church, school. Here's a 70-foot level. We'll zoom into this area right here. So zooming into this area, the key has some numbers on there. And so one number is the in the red is the tsunami run up, the elevation of the extent of the wave. You can see the school is just barely above that. So the 70-foot mark. And then there's this direction of wave movement shown directed toward that portion. And the magenta number gives a number associated with the relative amount of damage, 1 being the least and 5 being the most, just to, as George Plafker and others had to kind of get some kind of numerical scale to assess the damage they observed throughout southern Alaska. And so that particular 4 refers to trees larger than 8 inches diameter broken, uprooted, overturned, boulders thrown above extreme high water line, all structures and equipment damaged or destroyed in inundated areas, which is what happened here. Maximum run-up height of 70 feet. So that's right at the limit here, 70 feet of this level 4 damage. And this is kind of going forward in time to the 2016 study. We were looking at Chennai Cove and Chennai Village, this community, this one community in the area that was here. And you know, in part, the loss of life and near total destruction of this area led to kind of push to understand the science of how this happened. And this shows a nice rendering. Color is water depth. So the deeper blues and purples are the deeper portions and the hundreds of meters below sea level, and the shallower regions are in red near the coastal areas. And these dashed lines show where the authors have figured out where the landslides came from, what portions of the steep slopes fell, where did they get redeposited, and that gives an idea of, you know, how it would have been that action that generated these waves in this area that caused the devastation at Chennai. Moving west out of Prince William Sound to Seward is the last stop in the tour of local tsunami effects. Here's our fjord picture again, this multi-beam bathymetry map looking at the depth, water depth, the blues being in hundreds of meters deep, the reds being the ones near the coast. But like with most cases, as it says bathtub, it's a steep walls, pretty steep walls going down into this flat bottom. And it's the instability of the slopes on here that ultimately caused these submarine landslides to create local tsunami waves. So here we are, Seward Resurrection Bay, 1960 census population was 1891, and 33 deaths occurred in Seward from the 1964 tsunami. Here's an iconic photo from the 1964 earthquake. You have a boat stranded, you have an oil truck just obliterated here, Texaco, torn up docks strewn with logs and scrap metal. Another shot, just it's tough to see, especially with the despondent fishermen here in the photo of what is probably a fairly devastated boat in a tough place from the tsunami. I got out some Google Earth images from today just to kind of get a picture of a lot of these places are still there, just quite different from what they were back then. So we'll try to understand, especially if you've been to Seward, get some perspective on what happened there during the 1964 earthquake. So here's Seward today, and I'm going to sort of bring in the transparency of Seward at the time in 1964. And so here we have Seward just before 1964. I've kind of indicated the Alaska Railroad dock, Standard Oil Company tanks. There's a structure here in green, and in the margin of this composite image, there's some other oil tanks that we'll see in other photos. So this is from my USGS report in 1967. So I'll go right back through that just to say here's Seward today. And, you know, keeping your eye on what's no longer there. We can see on this shoreline here, we don't see oil tanks or railroad dock, things like that. But here it was in 1964. Tanks, lots of tanks actually. and then this railroad dock. So that's before 64. The question is what happened after 1964. And so here's the after. So they're as close as I could make to aligning these. Here's the before, here's the after. And what you'll notice, I've left these items so you can line them up a little bit. This shows this white line. The author showed where the tsunami maximum height reached by the waves is shown right in here along this line. And it goes all the way up in here. And so it's actually to the east, but to the downside of this photograph, you can see there's a lot of just darkness. And the darkness is, the snow's not there, but the structures, the reflective materials aren't there either. These docks are not at all in the same condition. And you can see extensive damage, and the actual shape of the coastline doesn't even, we'll see it's a lot more scalloped after this destruction. So here's before 64, after, before, after. So we'll look down at some of the detail here. So here's the same pictures. You're looking at a different perspective, but we had these two sets of oil tanks here and here, the small boat harbor. This is before 1964, the railroad buildings over here, just giving another picture of what things look like. Pretty industrial, railroads, oil tankers, boats in here. And this is now looking the other direction, but here's the magenta oil tanks, and there's this extremely modified shoreline. You have railroad cars just thrown about like, toy trains in here. So I'm going to go back one. So here's the railroad yard. This is the magenta tankers on one side. These are the red ones on the other. And you can see this shoreline is completely modified, destroyed by the 64 local tsunamis. And so here you can see this shape, this scalloping shape is showing this permanent alteration of the shoreline, and likely the source of material that actually was lost and went deeper down into this fjord and created the waves that would have come back and caused some of this damage. So yeah, we'll see some local close-in pictures in these regions. Here's a car next to a train with tracks that are bent, trains knocked over. That's the impact of these tsunami waves. And here's a truck at Lowell Point, 2 miles from Seward, bent around a tree by the surge waves generated by the underwater landslides. The truck was about 32 feet above water level at the time of the earthquake. So just another mark on kind of man-made structures to impress the point of these effects. In this case, local tsunami waves caused by submarine landslides, caused by strong shaking from the earthquakes. Finally, we get to our takeaway topics after this third Part C video. Tectonic tsunamis are caused when a large region of the seafloor moves up or down, which generates a wave that can propagate across the ocean. And it can be a few waves. It doesn't mean that there's just one wave, as we've seen from the receiving side of these places. Local tsunamis may generate much larger waves, but they do not propagate beyond several kilometers. They're generally caused by underwater submarine landslides that are caused by earthquake shaking. The majority of the deaths in 1964 were caused by tsunami waves, not direct effects from earthquake shaking. The majority of the tsunami deaths in 64 were caused by submarine landslides, including at Valdez, Whittier, Chenega, and Seward. A minority of the tsunami deaths were caused by the tectonic tsunamis, such as reaching Crescent City, California, or Kodiak. Without the glacially carved fjords in Alaska, there would not be any significant submarine landslides. It's worth making this straight point because it shows some of the unique aspects of being in an earthquake setting with glaciation or former glaciation. Finally, earthquake waves travel in the solid earth much faster than tsunami waves travel in the ocean. So if you feel strong shaking in a coastal area, head for higher ground. Thank you for watching. Please check out the other Alaska earthquake science fact videos, and we'll move here to the endnotes. There are a lot of endnotes. So first we have a set of general endnotes on tsunamis, links to some of the videos, looking at the Alaska Earthquake Center tsunami portal for looking at inundation maps in different parts of Alaska, how to use it. You can also look at the Alaska Earthquake Science Fact video on the 1946 Aleutian Islands earthquake. Thanks to Elena Suleimani for discussions and feedback. The section on tectonic tsunamis for the 2004 Sumatra Andaman earthquake in Indonesia. Also tectonic tsunamis for the 1964 Alaska earthquake. Endnotes on local tsunamis, the 1964 Alaska earthquake. Also some references related to glaciers carving landscapes. This is all credits for the images used within these slides. And as a final slide, just to say a reminder that the magnitude of very large earthquakes is actually a fairly challenging topic. And I was just showing for the 2004 Sumatra earthquake, you'll see things about 9.0, 9.1, 9.2, 9.3. We've gone with 9.2, I would say is the prevailing magnitude. But if you look at the USGS site, they will show 9.1. Thank you again.